I spent the last couple months working on a brand new board for robotics. It is a DC-DC converter that goes from 24 volts to 5 volts with an emphasis on high current capability and output stability. Hi again, it's been a while, but I've been working real hard since last time, and I'm really excited to showcase, like what I did since then. I suppose the first thing to address is why we're doing this in the first place. As a robotics club, we build a Mars rover that competes at international competitions. The one we go to is called CIRC, the Canadian International Rover Competition. And basically, on our rover, we have two chunky 24-volt batteries. So that's one thing. Now, we also have a Raspberry Pi on our rover to control the robotic arm mounted on the front. So this Raspberry Pi needs 5 volts. Now, the question is, how do we get from 24 volts to 5 volts? I mean, we answered that in the past pretty easily. We took this chunk of aluminum DC-DC converter found on AliExpress, and it's worked out pretty well so far. Up until this year's competition. Because at this year's competition, we were seeing a crazy amount of instances where the Raspberry Pi just shut off out of nowhere. Like there's no apparent reason. Now, higher command, upon the post-diagnosis, they decided that, oh, this is a power stability issue. So hence, we need to make a custom solution that's better. And, that's why I'm making this board. So this is what my board actually looks like. It's about the size of a slice of toast, and I don't know, let's go through it. At the top, you can see a Molex connector. It's a big connector, okay? There we have our grounds and our 24 volt and 5 volt input and output. These power lines go down to the bottom of the board where the power conversion actually happens. So the principle of a buck converter lies in this. You have a voltage input that gets chopped up. And by chopped up, I mean there's a switch separating the input and output that turns on and off many times per second. So at the output, you have high, then low, low is nothing, high, nothing, high, nothing. That if you look at it over time is like chopped up, up, down, up, down, up, down. Now, at the output, you also have a network of passive components like inductors and capacitors that smooth out the output, which is great. So at the end of the day, you have a lower output and a higher input. So you go down, step down. That's the goal of what we're trying to do in the first place. And it's implemented, as you can see on the bottom, with this IC from Texas Instruments. Basically, it is the one that controls the switches. You can see the MOSFETs on the left. Those are the switches that I'm referring to in the description. Now, our passive hardware that smooths the output is composed of this huge inductor along with the capacitor array on the output. So the reason why the inductor is so ginormous is it's twofold, okay? So first of all, we're dealing with a nominal current capability of 10 amps, and that's a lot of amps, and the inductor has to be big accordingly, so as to not heat up like the core of the sun. Now, the second reason why is because using a bigger inductor actually gets you better efficiency. Now, let me explain that point, right? So, an inductor effectively stores current, right? Now, a bigger inductor logically stores more current. So, leave that as it be. Now, the second thing that's important is that the process of switching itself inherently wastes energy. As in, every time you switch, you're losing a bit of energy that you kind of want to keep. So, using a bigger inductor allows you to have longer times between switches so that you can have an overall smaller switching frequency, which saves you energy, which is pretty fantastic. So that was a lot of explanation, but I just feel like I had to explain the sheer enormousness of that inductor. So that's the main function just explained. Everything else is auxiliary. Like we have capacitors on the voltage input as well to smooth out the input. We have a switch on the bottom of the board to turn the system on and off. We also have a network, not a network because they're kind of like individual. We have many passive components to the top and bottom of the IC to configure the various parameters of the chip itself. Moving upwards, you might have noticed a hodgepodge of components and one small IC in the center. Because USB-C power supplying, especially in the context of when you're using a Raspberry Pi, is extremely convoluted in the sense that you have to constantly advertise from your power source, like with a signal, that you are capable of delivering 5 amps at 5 volts. The last thing I wanted to mention is my layer stackup. So I have 4 layers on this board, right? The top and bottom are for signals and routing, and the middle 2 are the ground planes. So one of them is analog ground and the other is power ground. The reason why I'm separating them is because the high frequency signals that are going through the power ground would absolutely obliterate the sensitive analog components, or at least their signals, on the analog ground. And of course, I'm tying these 2 ground planes together at this point in the board because having 2 separated ground planes is, to be honest, a horrible idea. And I know that firsthand. So that's about all I wanted to explain today, technical wise. I mean, of course, it goes a lot deeper than that. I'm not even, certain about a lot of these things. I'm mostly just copying what Texas Instruments has on their layout examples on their datasheets. But I did write a documentation, like I said before. It's linked below. Please click. It's really cool. And yeah, the next video is going to be on testing and assembly, and it's going to be a hoot. So you should totally watch that. But yeah, have a good one.